In this video, we will continue discussing about the topics on dynamics of electricity. This is part 2. Our part 1 is talking about the current that flows into the conductor wire. So in this topic, this video, we will study what will be the resistivity and the resistance of the wire conductor. Okay. So in order to study this one, we need to include the Ohm's law principle. So that's it. We will start. Now, resistivity. If we consider a conductor, imagine this is a conductor with a cross-sectional area of A, then take note that we use the conductor in order to transport the electrons. So we will provide potential difference on this wire. So if we have potential difference higher on this side, potential A, and we have potential B, then electric field will be from high to low. So therefore, this will be our electric field. Now take note, in our previous video, in video number 1, the current also will flow from positive towards the negative in the direction of the electric field. Okay? So current is what? It is the motion of the charge per time. So it should be coulomb per second. That's why the unit of current is ampere. Okay? If we divide that I with the cross-sectional area, the answer is the what? Current density. Okay? The current density. So we have the current density which is J. Okay? So what will happen if we divide E with the current density? The result is resistivity. Okay, this is the meaning of resistivity, which means that the resistivity is directly proportional to the electric field and inversely proportional to the current density, or the resistivity is proportional to the ratio between the electric field and the current density. Take note, the current. Why is it that there is electric field? The reason is because we connect a source charge from high to low. For example, we will place the positive potential here and this negative potential. So therefore, we have the potential difference. Because of that potential difference, we can produce electric field. Okay. Remember that electric field or the potential difference is the product of the electric field times the length of the conductor. So therefore, why is it that we have this electric field? The reason is because we introduce a charge on the both sides of the conductor. Okay, so take the ratio of that the electric field divided by the current density. Take note, what's current density? This is the current I divided by the area. Okay, so this is the definition of resistivity. Now, what's the unit? What's the unit? So the unit is, take note that electric field is what? It should be volt per meter. Why volt per meter? Now, take note, in our previous videos, remember that the electric field is the potential difference divided by L, or the potential difference is the product. Okay? If you multiply the electric field by the length between the charge, because imagine a charge here positive and a charge here negative. So, same charge. So, therefore, the electric field within should be the same also. Okay? So, therefore, it should be the potential difference is equal to the product of the electric field times the length. Just like parallel plates. Okay? Parallel plates. So, therefore, the unit should be volt per meter. Why? Because this is potential difference unit and this is the length of the conductor. Okay? So, that's why this is volt per meter, because the unit of uh, potential difference is volt. Okay. So then, what is the unit of current density? Remember, current density is I over A. So it should be what? It should be ampere, okay? Ampere per meter square, because A, the area of the conductor, cross-sectional area, is meter square and is I. And the unit of current is ampere. So therefore, you have to divide this one. Take note, we want to measure what is the unit. We want to know what's the unit of the resistivity. So do it this way. So take note, this is fraction. So therefore, copy the numerator, then invert the divisor. Okay. So invert this one. That's it. Then we can cancel this meter. So this will becomes meter only. This will be cancelled out. Okay. Now take note that the volt, this is volt per ampere, is ohms. Why? By the way, this meter is coming from, this is risotto, this is meter, cancelled out. Now, if you divide the volt unit with ampere, the result is ohms. This is Ohm's law, okay? This is Ohm's law, actually. Later on. Okay. Take note that E is electric field. The unit should be Newton per Coulomb, or this is volt per meter. There are two units of the electric field. Then the J is the current density. The unit is ampere per meter squared, and the resistivity is ohm meter. Okay, so we will uh, go back to this definition. Why is it that this is volt per ampere later on? Okay, so by the way, take note that the resistivity is a property of material. Means this depends on the material. This depends on the material. So therefore, if you take the electric field, because the electric field, take note, the current depends on the electric field, and the density depends on the current also. So therefore, the ratio will vary. But if you divide electric field by the current density, this is always constant to the same material. Which means that if you increase the potential difference, you are increasing E, then you are also increasing I, and you are increasing J. So if you divide A with J, the result is always the same, and we call that as the resistivity. Now, these are the result of the experiments at room temperature 20 degrees Celsius. The silver is 1.47 times. This is taken from the book of Young and Friedman. These are the from the table. Silver is 1.47 times 10 raised to negative 8. Copper is 1.72 times 10 raised to negative 8. The unit is ohm meter. Take note, these are the resistivity. By the way, the resistivity means it is the ability to resist. Take note that we want the conductor in order to convey electrons, but materials have different characteristic. So within the materials, there are materials that a good conductor, a poor conductor. So poor conductor is insulator. Okay. So therefore, the resistivity also varies. So from the word resist, it will resist the current not to flow. So you can imagine water flowing towards this direction, and the resistivity is this one. So it will oppose the flow, which means that if your if your resistivity is greater, then the flow of current will reduce. Okay, the flow of current will reduce, or the flow of electrons will reduce also. The energy is water. Just like if you are if you are okay inside the tube or the pipe wherein water is flowing against your direction, so you will find difficulty in transporting yourself because you are against the flow. Okay, so if the current is flowing in this direction, take note that the resistivity is always resisting the flow, because the purpose of that is resistivity is to hold the electrons not to move from the conductor. That's why when you look at the silver and the lead, for example, which one have greater resistivity. So the greater resistivity lead. Okay? Which means, by the way, these are arranged in according to the ability to conduct. The good conductor is silver, followed by copper, gold, aluminum. So these are good conductors. Now, if you continue this one in the book, this is going to insulator already, and the number is increasing its magnitude. So the greater the resistivity, what? The smaller the current to flow. Okay? So, if you have a very, very small resistivity, then it is a good conductor. You can imagine soldiers. Okay? There are many soldiers. If there are many soldiers, then the opponent will find difficulty in uh, moving towards place. Pero if there are only few soldiers, then they can easily penetrate. So therefore, when we say conductor, if it is a good conductor, then there are only few soldiers inside. If it is insulator, what does it mean? Insulator did not allow the current to flow. So why is it that the electrons cannot flow? The answer is because of the resistivity. There are great number of resistivity in an insulator. Okay? So again, these are the values. In case of problem solving, you have to memorize these constants in order to solve the problem. Take note that we relate the resistivity in terms of electric field. And later on, we will relate this electric field in terms of voltage. And this one is, we will relate this in terms of I. So therefore, we will involve the resistivity. And we need the value. And take note, this is at 20 degrees Celsius. Okay? Degrees Celsius. Meaning this is the room temperature. Which means that if the temperature is very high, then you cannot use this one. Approximately, then, but take note, the resistivity will differ with temperature. It varies with temperature. So, the temperature and the resistivity and the temperature of conductor relationship, what will be the relationship? This is the formula. Which means that in our table, this is only for 20 degrees Celsius. Suppose the temperature of the wire now is 40. Is it the same resistivity? The answer is no. Okay? The answer is no. The resistivity will change with temperature. Okay? So therefore, this is the formula now. This is the temperature. This is the temperature as a function of the resistivity as a function of temperature. Means when you say 40, what will be the resistivity at 40 degrees Celsius? So the formula is this should be the rho. The rho means what? This is the resistivity at the reference. Our reference is the 20 degrees Celsius data. Okay. So therefore, this one is multiplied by 1 plus, this is empirical formula, plus 1 plus, this is temperature coefficient alpha, and multiplied by the final temperature, which is this one, and this is the room temperature. So therefore, if you use the table previously, therefore you have to use this, you have to use the 20 degrees Celsius. Okay. So take note, these are the tables. You need this one. Why? Because we want to know how much is the resistivity at room temperature. And after that, wait, this is not the resistivity. This is the temperature coefficient. Okay. Take note, this is constant. Therefore, for every material also, aside from the resistivity, we have the temperature coefficient. And the unit is per Kelvin or per degree Celsius or Celsius degree. The unit is per degree Celsius. This is alpha. And this is the alpha. Take note of this. This is the temperature coefficient. And T, again, is the actual temperature. While T naught, okay, this is the reference temperature. This is at 20 degrees Celsius if you use the table. If there are other reference, then do it. But you have to specify or use the specified temperature. In this case, these are the available data we need to use. Okay, so this is 20 and this is the target temperature, and this one is taken from a table. So therefore, for example, if you use carbon or copper, then use the 0.00393. If you're silver, then 0.0038. So I think you have to memorize this one if you want to solve the problem. So, for example, you are asked, how much is the resistivity at 50 degrees Celsius of the copper? Okay. What will be your answer? So therefore, all you need to do is to, again, this one will be obtained from the table of resistivity at 20 degrees Celsius. Then this is the temperature coefficient, and this is our target temperature. Then it should be 20. So therefore, you can always solve the resistivity. So memorize this formula. Okay, resistance. We are now on the resistance. We notice we studied resistivity, then this time resistance. Now resistance is the this is not the amount of the resistance value of the conductor. So therefore, because the if we have the resistivity is just a property of material, but the resistance, it is now measuring the amount of the resisting force. Okay, it is now directly proportional. The greater the resistivity, the greater the resistance. But take note, we have it varies with length and it varies with area. So therefore, what is now the formula of finding the resistance of the conductor? Because take note, we will find the resistance of the conductor. So this is not the conductor. And take note that the resistivity is constant because if say copper, so therefore the resistivity is the same. But this length will keep on changing. Okay? And this one, area is also changing. So what will be the resistance in terms of area and its length and its resistivity? Because resistivity is talking about the material. And area, positional area and the length is talking about the physical dimension of the conductor. Okay? So, let's start with the definition of resistivity. Again, we will work on this problem. Now, if we take the diagonal product of this, the electric field now becomes rho J. Rho means the resistivity, J means the current density. Okay. Now, take note that the electric field here, as I've said in the previous slide, the electric field is what? Is equal to what? The potential difference divided by L. Okay, this is the potential difference. Remember our parallel plates formula. The voltage, potential difference of the parallel plates, the voltage between at a distance d is potential difference. Electric field is constant inside times the distance between the particle. So in this case, electric field is constant because it is now in the conductor. So it varies now with the charge at both ends of the conductor. So therefore, this is okay. Now later on. So, but what is I? I is V. What is J? J is I over A. Take note. But this one again is B over L. This is the electric field. So therefore, we replace electric field by V over L and we replace J with I over A. So what will happen now is we can cross, we will transform this one in such that this I will be placed here and L should be here. So therefore, this will be the result. Now, analyze clearly the result. Take note, this is potential difference, means voltage, divided by the current. And this is rho, which is the density, times L divided by A. Now, what is V over I? Okay. This Ohm's law. Okay. Voltage divided I is Ohm's law, is R. If you divide voltage by the current, the result is resistance, R. Okay? Or, we can say that what? I is equal to V over R. Or, diagonal product, V is equal to IR. This is Ohm's law. Okay? This is Ohm's law. So this proof is allowed only provided you have to follow the unit of consistency. So what is now the unit of voltage? It should be volt. What's the unit of the current? It should be A, because this in honor of Andre Marie Ampere. By the way, the unit of volt was given in honor of Alessandro Volta because of his invention of the voltaic cell. Okay, so voltage is unit of volts. Then R is ohms because the resistance is George Simon Ohms. He was able to study the resistance. So in honor of the principles of the Ohm's law, then resistance now is in ohms. Okay. So therefore, the consistency of this Ohm's law should be R should be in ohms, voltage should be in volts, current should be in A. This is resistance, sorry. This is the current. This is not resistivity. Is current. Okay. This is current. Okay. So therefore, we can say that look at this one. The 1 ohm should be equal to 1 volt per ampere. So therefore, the ohms means volt per A. So that's why, if you remember in a previous slide, why is it that the unit of resistivity is ohm meter? Because the voltage over A in our previous slide is equivalent to ohms. You can go back the previous slide. So it is actually coming from the Ohm's law principle. So therefore, we can say that, look at this one, I, this is ampere. Okay? So ampere should be what? 1 ampere is equal to 1 volt per ohm. Or this one, 1 volt is equivalent to what? 1 ampere omega. Okay? So 1 omega ampere or ampere omega. So this is the meaning of 1 volt. So again, this is okay. Going back to this problem. So therefore, this will now what? This will becomes R. So R is equivalent to the resistance value of the conductor now is rho L over A. So the resistance of a conductor is directly proportional to the resistivity, meaning the greater the resistivity, the greater the resistance. Okay? And it is directly proportional also to the length, which means that if you have large length, then the resistance now is keep on increasing. But it is inversely proportional to the area. What does it mean? If your wire is has a greater area, okay, meaning if your wire is of a greater area, then it follows that your resistance is small, okay, because it is inversely proportional. For a small area, the resistance is big. Okay, so therefore, take note that if your wire in your house if you have extra wires and it was connected through the source, then take note, you have a large resistance. Now, take note, resistance is to resist the flow of the current, which means that if you are using extension wires, then you are consuming a lot of energy. Why? Because large wire have a large value of resistance. And the resistance, remember, is countering the flow of the current, which means that you are consuming energy more. So, avoid using very large extension wire. Make it short. Okay? Why? Because you are consuming energy in that. And take note, is it inversely proportional to area. Okay? The wire, thin wire is dangerous to the, but because remember, smaller wire carries only small current also. So therefore, the wire should be followed according to the specifications of the uh, electrical specifications. Do not easily use the wires without the prescriptions. So usually, small wire, it has a large resistance. So, okay. So therefore, R is the resistance in ohms, L is the length conductor, rho is the resistivity area. The conductor is meter squared. Okay. Now the resistance also varies with temperature. So therefore, you can use the previous formula. Because take note, if the resistivity varies with temperature, the resistance also varies with temperature. So almost the same, no? Okay, so therefore, okay, you have to use again the table. Oh, what is RO? RO means the reference R. So you have to use this formula. Okay, because we have no table for R, but we have the table for the resistivity. So therefore, your R reference R now is the reference resistivity over LA. So use this table because the table here, this is your R naught or the reference. So therefore, identify your length of your wire and your area, divide it, and multiply these values. If you are using copper, for example, then you can solve for the reference R. Okay, so this is the reference at room temperature 20 degrees. So then this is the target temperature and this is the reference temperature of 20. So we miss R naught here. R naught means the reference. Okay, so then this one is the same as the previous table. So if you are using copper again, 0.00393, you have to use it because the most common conductor in our household is copper because affordable cost and available materials. Okay, so it solves this problem. A wire has a square section. So imagine a wire has cross section of 2.3. Then the length is 4 meters and carries a current of 3.6. So therefore, there's a current on it. The density of the free electron N, remember N in our video number 1, 8.5 times 10 to 28. This is per cubic meter, sorry, this should be minus 3 per cubic meter. Find the magnitude of the density, current density in the wire. So J, what is J? So for this solution, J is I divide A, okay? I is already given 3.6, so substitute it here. What is area? Okay, this time area, take note, this is square cross section, and this is the side. So this should be 2.3 times 2.3. Then convert to meter. So you have to substitute here. So 2.3 convert to meter should be times 10 to the negative 3, then raise it to 2 because square means the square of the sides is the area. So then the unit should be ampere meter square. So therefore this is the answer. Large number, okay? Because this is a very, very small number. So 680,529.30 ampere per meter. This is the answer for letter A. Letter B. Letter B, you're asked to solve for the electric field. Take note E, okay? So E is present in the relation of the resistivity. It will be rho is equal. Okay, then A also is found in what? E is found in the voltage E times L. Okay, so in case you are asked what is the electric field, but the given is voltage. If given a voltage, then the voltage is also connected with the Ohm's law. So you have to work on the formulas in our previous slides. So in this case, you are asked to solve for electric field. Okay, so all you have to do is to diagonal product. Now, take note J was provided. Okay, now what is rho or what is the resistivity? Take note this is copper. Okay, Now, take note that in our previous, what is rho? Okay? So, copper is what? 1.72 times 10 raised to negative 8. So, therefore, you have to use this one 1.72 times 10 raised to negative 8 here. And this J is 680,528.30. So, then, result, the answer is 1.17 times 10 raised to negative 2 volt per meter. This is the unit of electric field. So, this is the answer, letter A and letter B. We still have the letter C. Letter C is how much time. Uy, you are asked to solve for the time required for the electron. Take note, the electron is flowing to travel the length of the wire, which is the length of the wire is 4 meters. So 4 meters. This 1 meter. So 4 meters of wire. How many seconds or hours or days that electron travels from one end of the 4 meter to another end of the 4 meter? And the diameter is 2.3. What do you think? How fast is the electron travel on the 4 meter wire considering this current of 3.6 ampere? Okay. So imagine this is the wire and the area is 2.3 times the square of this. Okay, this area and the length is 4 meters. Take note the electrons is traveling on the conductor. So we use the electrons. And take note the electron is travel inside the conductor. So the speed is called now the direct velocity. Please go back to our video number 1, the discussion on direct velocity, BD. Take note that molecules are keep on moving and translational or in the direction of the conductor very slow. It is a very slow, very fast within the materials, but when in terms of translation, it is a very slow flow of electrons. Okay, so therefore, if it starts from this point, then it will move until to the end point. So, how much time? What is t? Okay, so to answer is you have to use the formula in mechanics that the initial velocity is the displacement over time. Our displacement is L. Our time is the required time. Velocity is the drift velocity. Remember in our previous video, we can calculate the drift velocity. Okay, in terms of what? In terms of current and the number, the free electrons. This is free electrons, and we have the uh, charge of the electrons. Okay, so therefore we can calculate this one. Nothing to worry. So diagonal product of that, then T is equal to L over D. So L, nothing to worry, but this one we don't know the answer. So all you need to do is to use this formula. Remember in our first video, I is the charge concentration times the charge of the particle. Our particle is electron, so therefore nothing to worry. This is 1.602 times 10 raised to negative 19. Okay, this provided. This one is also given. You have to square this one because square sections. Okay. Then this one is unknown. I is given. Is 3.6. So take the solve the velocity in terms of I and in QA. So therefore I is equal to in QA divide. So substitute the values. 3.6 for the current. N is the concentration. This is the charge of the electron and this is the area of the wire. So calculate again. And the drift velocity is a very slow 4.10 times 10 raised to negative 5. Okay? Very slow. So then substitute. Use again this one to solve for t because the required how much time required. So L is 4. Divide this one. So do it. Calculate. According to this result, 80,037.7 seconds consumed from traveling from one end of the wire in a 4 meters towards the end. So if you convert this to days, approximately 22 days before the electrons arrive at the other end of the 4 meter. Okay? So these are the answers to this problem. Again, you can always answer problems provided that you know the formulas and you know the principles. So if you understand in the previous video until today, in any problems, you can always solve. Okay? So this is a good practice. This one again. Problem practice number one. Then number two, use your previous knowledge from video one, the current, and this video number two. Now, if it involves, remember, if it involves voltage, then you have to use the Ohm's law and the relationship of voltage with the electric field. And the electric field is connected with the resistivity. And the resistivity is connected to the resistance. So everything was connected. Resistance is connected to voltage. And the voltage is connected to I. So they are connected to each other. So therefore, in terms of questions, for example, look at this number one. You are asked number three to solve for the potential difference between the 2 points of the wire. So how will you answer that one? You can answer that using the electric field and the length. Okay, you can also that you can use also the voltage, potential difference using the Ohm's law. It is I times R. So if you have I and you have R, you can solve the voltage. So again, you have to rotate everything in all the formulas. Then you can. This problem now becomes easily to solve if you know the concept on the video one and the video two. Okay, so that's all. Thank you for listening.